Hi everyone. So here we are with a continuation of aldehydes and ketones. Our focus here is on how to apply what we've learned so far. So we've got an aldehyde or ketone, in this case a ketone, and when we react it with something like ethylene glycol, we end up with a cyclic acetal, okay? And we lose water in the process, and because here's a H2 and an O from the carbonyl. But if we use acid and water and just a catalytic amount of acid, we can turn these parts into then the hydrate, which then is reversible with the carbonyl, and the carbonyl is favored. Okay, as long as there is not a terrible excess of water in solution. All right, so we can use that to our advantage. But before we learn how to use that synthetically, let's just practice sort of going back and forth. So from the carbonyl, we go to the acetal. From the acetal, we go back to the carbonyl. So here's some practice problems from Klein. And we're using H3O plus, which is H plus and water. And we're using it to convert this to the hydrate and then back to the carbonyl group. So let's do one of these together. Basically, you can picture that this acetal will get protonated by this acid, and we will end up with a leaving group then, and something like this then. And you'd have the water that's in solution coming in and releasing this group. Now, they're not asking for the mechanism, but I'm just going to show you how this works so that you understand it better. So that's always a goal, right? Is to try to understand it better. Okay. So at this point then, I'm going toward a carbonyl. And I know this is probably going to involve some kind of a hydrate intermediate. So I'm going to hydrolyze this off with water. I'm going to try to get rid of this ethylene glycol here. So to do that, I attack it with water, and then I do a proton transfer and try to make this a good leaving group. Now, a lot of people like to just use this as their acid, but most likely you have a lot of acid floating around, so it probably just gets protonated like this, honestly. But if you like to show it the other way, that's fine. I'm not too picky about it, even though some people might be. Mainly, I just want you to understand how it works. And also, there's water here to deprotonate there. So this is very common for us to do proton transfer, where one site grabs the proton, the other side gets deprotonated. All right, at this point, you can see how the sort of looks like a hydrate. And actually, I don't have to use another water to attack here. I could just, in fact, do this sort of a tetrahedral intermediate where this comes in and then this leaves. So I can get the protonated carbonyl group right here. And I have ethylene glycol that just left. This right here is ethylene glycol. And it just has a bond rotation, that's all. And then I've got this group here, and then I just use another water and deprotonate there. So I actually end up with the carbonyl version of this. So there it is. I'm going to go ahead and just get rid of all this then, and I'm just going to show that carbonyl that we got. Now you might think, wow, why do we do all that stuff just to get this? Like, you can just see it, right? You can sort of picture this group here just transforming into that group there. But I'd like for you to know exactly how that happens, because sometimes when it's not clear, you can make mistakes trying to guess what you're making. So it's not really guesswork. You can figure these things out. Okay, next thing, this is also an ester. It's just not a cyclic acetal, but this is an acetal as well. So you can imagine just switch this acetal out for a carbonyl group. But now you know the mechanism of how it happens, and you should practice it. So just like I did from here to here, you can practice from here to here. And you can take any of these problems and practice. Why don't you take a moment and think about these two, and then we'll do that together. All right, guys, we're back. For this first one, it's a little tricky, but it's sort of an upside down version of this one. So if I just rotated it, you might see the ketone is actually from this part, and then this is the cyclic acetal part. So what I'm really envisioning in this problem, sort of a reverse way of thinking about it, this is my acetal that comes off, and my ketone is based on that group. So it's going to be actually this. And your side product, which we don't always write, I'm sort of guilty of not writing these things out myself, but it's a good idea to do so. It's a 3-carbon unit propylene glycol. All right. If you're unsure of how that works, try the mechanism. It's the exact same mechanism as all of these. Okay, it's just different starting material. The next example is a little tricky. What I did was switch these two groups so that I could see the acetal a little bit more clearly. And that tells me that the carbon they're both attached to, these two OR groups, are attached to right here. It must be where the carbonyl would have been. Now the weird thing though is you can't really just break that off because you've got this R group here, and then you have this weird, like half of it is a cyclic and the other half is not. So it's a little bit of a weird problem. So what I did was I first just protonated one of these O groups. It doesn't matter which O gets protonated. I protonated here, for example, and I let that leave, generating the pi bond that I need for the carbonyl. Now, this methyl group is problematic, though, so we'll figure that out next. We have water attack and try to neutralize this, and eventually let this go as methanol, okay? And then the OH of the H2O that attack, that will become part of the carbonyl group. Okay, so that's the general thinking. So then, once the ring opens up, I did some numbering here just so you could keep track. 1, 2, 3, 4, 5, 6, 7, and then the OH group over here on the end. All right. So I need water to come in. This is H3O plus, so there's water there. I can break that open. The next part over here is to deprotonate this water, because this will ultimately be part of my carbonyl group, and to protonate this because I want this part to leave. When I have the OH group ready, then I could have water come in, grab the H, the bond between O and H breaks. I make a carbonyl here, and then I kick out the methanol, protonated methoxy group. And so, all right, so then that means that water will have grabbed the H. I have the carbonyl here. So this is a 1, 2, 3. And then I have the OH here, so it's a 7-hydroxy-3-heptanone, okay? 7-hydroxy, yeah, wow, that's a long name. And then methanol is what came off here. Could I have, in the first step, could I have protonated up here? Yeah, perhaps. I think you could see that that might work as well. So if you protonated here instead of here, it should still work. So you protonate here, you're going to let go of methanol. This will be the carbonyl, and then you'll have water attack and make this leave eventually anyway. Ultimately, these both have to leave. When this one leaves, it's still attached to the molecule, though, because it's a cyclic, this is the cyclic hemiacetal. All right. Okay, so you can imagine then practicing going the other way. How do I take this molecule or this one, and how do I make it into this cyclic hemiacetal? So I think you should be able to see how that's an intramolecular reaction, and we've done an example like that a couple of videos ago. All right, the next part of this is the idea of a protecting group. So we have, let's say, 2 carbonyl groups. We know carbonyls are the reactive groups we've been learning about. And when we have carbonyls, there's different reactivities. We learned in the very first thing in this chapter was aldehydes are more reactive than ketones. Well, now I'd like to add that esters are less reactive than ketones. So it's aldehydes more reactive than ketones are more reactive than esters. So if we have 2 carbonyl groups, it turns out that we can selectively react one over the other. And that's so because ketones are more reactive than esters, this group will react first, and then what that allows me to do is, maybe if I make this into an acetal, I can then do things to this carbonyl group, and then I can take the acetal off of this one and get the carbonyl group back. So that's the idea of a protecting group, is if I want to react this part, maybe I protect this carbonyl so it doesn't react, then I do my reaction, and then I let go of that. So I'll show you an example of that right here. So first step is identifying, who's more reactive. If you see multiple carbonyl groups especially, we see that the ketone is more reactive. So that's going to be ideal to protect the ketone and then do your reaction over here later. So we'll do that using ethylene glycol. So we get this, and then after ethylene glycol and acid, we get our protecting group there, because the ketone is more reactive than the ester. The ester is left alone. Now after this step, what this enables me to do is to say, oh, so that ketone can't react anymore because it's not a ketone anymore, it's an acetal. So, but this carbonyl group here is sensitive to certain reagents such as Grignard, lithium aluminum hydride, and things like that. By the way, I generally wouldn't use sodium borohydride, NaBH4. That's a common reducing agent, but mostly for ketones and aldehydes. If you're more oxidized, you need a stronger oxidizing agent like LAH. It's sort of like the way we use PCC as a milder oxidizing agent than Jones reagent, for example. So anyway, I don't want to use NaBH4 here. Let's say we use something like LAH. So in that case, I have, LAH. I sort of think of LAH as a shortcut. I think of it as hydride ion, but technically it's not, but there we go. Okay, now you can imagine the tetrahedral intermediate, and then you could bring that back down and kick out the OR. I'm just going to show you to do that in one step, even though I prefer for you not to. On exams, I like to see the tetrahedral intermediate, but for our purposes, I just want to sort of use it as a way of figuring this out. So not really doing a formal mechanism per se. All right. There's my hydride, and that's actually with one equivalent. Normally, we like to say excess because it's very hard to stop it at aldehyde. You can imagine if one of these molecules reacted, then the rest of the hydrides would attack the aldehyde rather than another ester, right? So it's very hard to stop it there. So regardless, sometimes they forget to say excess, but you sort of should know that it's implied here. Okay, so we've got that, and it's going to keep reacting because it's still a carbonyl that is sensitive to reduction with hydride. Ultimately, after acid workup, well, let's do before acid workup, we have this. Okay, so I think everyone's pretty comfortable with these reactions so far. I hope you are. Next, then, we have H3O+. Now, we know H3O+ will protonate here. Okay, so that will become OH neutral. But then we also know how H+ can affect this acetal, right? You guys just saw in the last example that it turns acetals into carbonyl groups again. So what's going to happen here is the final step will be to convert this back into the carbonyl group. So that's after step 3. All right, so your final answer is this. Now, why is it called a protecting group? This part right here. This part is called a protecting group because it's protecting my ketone by temporarily converting it to an acetal. It doesn't always have to be an acetal, but just the idea of it is to convert it to something that you can then convert back. Okay, so here, this converted to here, thereby sort of protecting it because then later I can bring it back. And so this was untouched by the hydride. If I did not protect it, you would imagine that this would be the first to get reduced. And so we would probably end up with, a combination of, first all of these would get reduced, and then eventually the ester would get reduced as well. So most likely we would end up with something like this. So it turns out that cyclic acetals, you can see that they're affected by acid. They convert back to their carbonyl. But fortunately for us, they're not as affected by base. So we can have basic solutions like Grignard and hydride reagents, and the cyclic acetal is pretty stable to that, meaning it'll stay. But keep in mind, if you had acid and you don't want to get rid of your cyclic acetal, then you're in trouble, because cyclic acetal is very sensitive to acid. Of course, that's how we remove it. So just keep that in mind. That's what this note is about. Explain why this synthesis does not work, and how would you perform this? How would you perform this synthesis in that case? So go ahead and take a look at what's going on here. I have 2 carbonyls, so maybe this is a place where I could use a protecting group. And notice that here there's no protecting group; they just go right in. And oh, sorry, typo. This is a CH3Li. Sorry about that. So basically, think about, well, why doesn't this work to make this turn into this? And then how can you maybe use a protecting group to make that happen? Okay, so let's figure out what's going on here. Clearly, this methyl lithium would love to attack the more sensitive aldehyde, more reactive aldehyde. But we show that it's not, right? So that's not right. Okay, so what we want to do maybe is react the aldehyde with a protecting group instead. So maybe I use step 1 would be my ethylene glycol in catalytic acid. Okay, and so that would, I'll just write over this if you don't mind. It'll make this weird, I call it a little alien. All right, so instead of the carbonyl oxygen, I have the cyclic acetal here, because the aldehyde's more reactive than the ketone. Then I could have this methyl lithium come in and attack my ketone. All right, so that would be my step 2. And then once that's done, I have an O- here with my methyl group from methyl lithium, just like I have right here. But then I need my 3rd acid workup step to get this onto here, and then also to change this back into there. Okay, so the sequence of steps: ethylene glycol in acid, methyl lithium, and then acid workup. This one's a little bit more complicated because it sort of looks at it backwards. So instead of starting with a carbonyl, we're using a carbonyl as like over the arrow. So let's look at how this happens. Right here I have a triol, so 3 OH groups. Notice they are making an cyclic acetal out of that here, okay, because these are in the right geometric position or structure to make a cyclic acetal. So this carbonyl group is actually over here now, and it's bonding like that, okay? Again, the mechanism would be these OH groups attack the carbonyl and so forth, okay? And we need H plus to activate that and to do a bunch of proton transfers and make the oxygen leave as water eventually, okay? Well, once you get that, and so you should know how this works. I would say if you don't know how this works, stop the video right now, pull out your paper and start drawing out how this works in acid to form the cyclic acetal. Okay. Now, after the cyclic acetal works, now look, this OH is free to react. So this is protecting the OH groups over on this end so that they don't react to hydride. Sodium hydride is usually used in the Williamson ether synthesis to make ethers. So it's called ether synthesis. So I take the hydrogen here, generate hydrogen gas, make this into an O-, and then I have this long chain, blah, 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 okay? And then you've got this electrophile, CH3I, methyl iodide, and then, one of these lone pairs can attack here, and I make my methyl ether. Once you make a methyl ether, then you've got that part of the molecule, like that, and then you have the rest of it But then you have this acid and water, which hydrolyzes it back to here, plus the original ketone. So you have now opened up, or deprotected the OH groups, the diol. All right. Hopefully I have this correct number of carbons. 1, 2, 3, 4. Yeah. Okay. All right. So I hope you see how it's the compare and contrast these methods. I think this is a little bit simpler to see, but do work through this, and it's just from the standpoint of the alcohols rather than from the standpoint of the ketone. You're using the ketone to protect the alcohols in this example. All right, here we are with some synthesis ideas using protecting groups, okay? So I'd like to go through one of these together, and then I'd like you to do the other two on your own. So for this one, I see that everything's the same except for this group. So I need to add an ethyl group. So maybe I will want to pull this off with NaNH2. And then, so normally you learned a triple bond. We'd use NaNH2, mainly for the NH2 part, because that's the strongly basic part. And then I would use ethyl bromide or ethyl halide of some kind to tack here. So I think you're familiar with these steps from OChem 2. Okay, if you're not, go back and review that. The problem with this is this could also attack here, right? Because this is also my electrophilic site in addition to this H, so it's the carbonyl carbon. All right, so how do I keep it from reacting here? Voila, we've been talking about protecting groups, so we try to protect that carbonyl group, and we know it reacts to make an acetal. So let's do that. So first thing we'll do is we'll use our handy, trusted ethylene glycol. So that will make this into a cyclic acetal. That will now leave this H here. There's an H here. Sorry, I don't have room to make it stick out. It should be sticking out. That's now going to be susceptible to our NaNH2. So that NH2 amide is going to grab here and deprotonate. Once you have the triple bond like that, the acetylide ion, and the rest of it, of course, looks like this. Once you have that, then the third step would be to get our methyl group, or ethyl group, ethyl group on there. Right, and your choice of halide, but go with big if you can, bromide, iodide, something like that. So ETX, and you can be specific, that's fine. Okay, so hopefully you followed that, and that involved using a protecting group. I have not taken the protecting group off yet, so you have to add step 4, H3O+. That converts it back to the carbonyl, which we need. Okay, so I'd like you to go through these and use the idea of the protecting group, and we'll go through it in a minute here. Okay guys, for these, they're pretty straightforward. They're very similar, in fact, to the example we did together here, as well as the example here. So the idea is we want to protect the more reactive one. We will then react at the less reactive carbonyl. And here, in this case, you can see we're adding phenyl groups, so it must be some kind of a Grignard reagent. Maybe like phenyl magnesium bromide. But before I do that, I need it to react at the ester, not at the ketone. So I better protect the ketone. Step 1, I'll do the ethylene glycol and acid. That will make this into a protecting group. Then I can do my phenyl magnesium bromide and attack here. But I need an excess. I need 2 equivalents specifically. You can write 2 equivalents, or you can write excess. And then step 3 would be to protonate this O, and also to return to my carbonyl, take the protecting group off. So that's what H3O+ will be for. This example is almost exactly the same, but instead of phenyl magnesium bromide, I need a source of hydride. Not any hydride. Usually we use LAH for esters because they're super oxidized. I need a really strong reducing agent. So I'll use the same stuff as before, except LAH instead of Grignard. Okay, hopefully you guys followed that, and if I wrote this, you should be able to show me after step 1, this is what the molecule looks like. After step 2, this is what it looks like. After step 3, this is what it looks like. Okay, so please practice that, and if you're not sure, come ask me questions about it. All right, the next part is very similar. You guys know from the periodic table that oxygen is above sulfur, and so they have a very similar reactivity. Okay, so you can picture we've done reactions with alcohol. So just replace the O with an S, and now you have a thiol instead of an alcohol. But it works the same way. The SH groups attack as a nucleophile, and then eventually this gets lost as water because we have acid in solution to help us with that. All right, so just like with alcohols, if we add multiple ones, we get an acetal. Here we add multiple ones, we get a thioacetal. Another reaction we use with thiols is thiol, instead of ethylene glycol, we have ethane thiol. Okay, and this can also attack here, and then this gets protonated, or this is protonated first, this attacks, and then this gets protonated, and this attacks, and this leaves, and so we have a cyclic acetal. Notice this could be used as a protecting group. Once we have the cyclic acetal, we can convert it back, we can actually reduce it using something called Raney nickel. So why would we reduce it? Well, it's just a different way of reducing. We learned about Wolff-Kishner, which takes this and reduces it to here. But if you have this group, oftentimes it's convenient if you are using it to do a protecting group, as a protecting group, then you can just reduce it right straight away. So turns out that this is another way to do what Wolff-Kishner does already. There's also another reaction called Clemmensen reduction. This is done in acidic conditions. So it's very common that when you have acid around, that it's more convenient to do this kind of reaction in acidic conditions. And if you're in basic conditions, or you have, let's say you have a protecting group and it's an acetal, and we talked about how it's sensitive to acid, then you don't really want to use Clemmensen reduction to do this reaction, right? You want to use a base so that your acetal is not affected by it. So, things like that are considerations that you have. So you want to sort of know what reactions can I do in acidic conditions that won't affect something that's sensitive to base, or if something's sensitive to acid, then I don't want to use acidic conditions when I try to do a reaction. Maybe I want to know the basic version of it. So here's a basic version where I have the Wolff-Kishner reduction with base workup right here. Okay, so it's good to, even though they're the same reaction, ultimately you have this group turning into that one, same thing here. The process and the conditions are different. And so if a protecting group is required, remember it comes off with acid, you might want to use Wolff-Kishner then. Okay, so that's why we provide multiple avenues for these reactions. Okay, so let's just try practicing, getting used to these two reagents. We've got a carbonyl group here. Obviously, that's the one that's going to react with this ethane thiol. At first, you may be like, what the heck? Sulfur? What's that doing here? But just tell yourself it's like oxygen. In fact, I wrote oxygen just now because I think of it like oxygen. Okay, so there's after step 1. If you don't know the mechanism for this, go ahead and review what it was with the oxygen, with the OH groups here. It's basically the same thing. All right, next would be Raney nickel. And Raney nickel, we learned, it reduces the thiol and replaces it with CH2 or H's. Okay, so after step 2, we're going to have just that. And we'll regenerate this. So you can see how that would apply here as well. The next reaction is called a Baeyer-Villiger oxidation. And this reaction is using a peroxy acid. So sort of like NCPVA. is another reagent. It's a kind of peroxy acid that you could use. If you remember, in the past we used MCPBA for alkenes to oxidize them into epoxides, right? Well, in this case, we're not starting with an alkene, we're starting with a carbonyl group. So we have a carbonyl group, then think of MCPBA or peroxy acid. It's just a really strong oxidizing reagent that puts an oxygen in your molecule, just like oxygen got inserted here. This time oxygen gets inserted on either side of this carbonyl group. Here's the mechanism for that. It's a bit detailed, and it's not super useful in terms of, it doesn't apply to a lot of different reactions. There's only a few handful that I can think of that is similar to this. But it might, for those of you who are curious, how does that work? What's going on here? This is nice that we do have a mechanism for it. So don't have to memorize it though. But it's this oxygen of the peroxy acid that attacks and then ultimately ends up in the molecule that results. Usually is a carbonyl group or ketone or aldehyde ketone, turning into an ester. So when you see that different transformation, it's Baeyer-Villiger oxidation, what could be. Okay, so the way that this works is often if it's a symmetrical aldehyde or ketone, then you just stick the oxygen in either side. But if it's asymmetrical and the two groups are different, then it follows a kind of priority system. And that is, for the most part, it's like with carbocations, where the more positive, the one that can bear positive charge better, like a tertiary or secondary, is more easily migrated because it sort of takes its electrons with it, can migrate. But turns out that hydrogen, for some reason, is the best migrator. And so let's look at examples of that. So here's an asymmetric ketone right here. And you can see this one is tertiary, in the sense that it has 1, 2, 3, or you can think of it as secondary, 1, 2. And so it's got a hydrogen here instead of a carbon. So just think of it as secondary. This one's primary, or methyl actually. This is just a methyl group. So I'm not counting the carbonyl carbon. Let's label that. All right, so when it comes to migration, that means if I have an oxygen inserted here or here, okay, that means that the R group will be able to migrate onto the oxygen better if it's in this order. So tertiary or secondary is better than methyl. So the oxygen will be here, and in looking at our mechanism, that means the R group that is secondary in our case will move on to the O. Okay, so that's why the O ends up here. Let's predict what the products would be then. So if I'm looking at this carbonyl and I'm trying to apply a peroxy acid, then instead of making epoxide, because I'm starting with a ketone, I want to stick an oxygen in here or in here. It will be according to the substitution of these guys. This is attached to 1 carbon, this makes it primary. This is attached to 2 carbons, so that makes this secondary. So it will be better to insert here. There we go, like that. And my goal is to make an ester. All right. Okay, go ahead and give these a try, and let's check our answers in a few minutes. All right, guys, so these are pretty straightforward. Remember, H is a really good migrator, and also not only is it easy to migrate, but you generate a carboxylic acid, which of course is resonance stabilized here. And also, if you remember, like PCC, remember how it oxidizes to the primary alcohol to an aldehyde, but other oxidizing agents oxidize all the way to carboxylic acid? Well, this is such an oxidizing agent. It will oxidize it all the way to carboxylic acid. So that is the reason why H is so, the oxygen goes in here is because it's easy to take an aldehyde to a carboxylic acid. They're sensitive to oxidation. Aldehydes are. Okay, and this last one, this side is more substituted than that one, so I will insert the oxygen in here. That makes a 5-membered ring into a 6-membered ring because oxygen is part of the ring now. All right, so for Baeyer-Villiger then, it's again one of our one-off reactions like Wittig and Wolff-Kishner, Clemenson. Sort of learn all your reductions together if you can, just to have context. But for things like this, maybe just write them out separately and write down little notes about them and just keep practicing so you don't forget. Why all that is important is because we're going to use it to do synthesis, so that will be in the next video. Until then though, please go back through what we've done so far up until this point from all of chapter 19. Go ahead and just summarize. Do I have every single reaction we've covered written down in a really simple form? Start learning those. Do I have mechanisms for them that I can use to apply to understanding what products I might make? Write down all the mechanisms you can that are helpful and useful and that I might test you on. Okay, so go ahead and go through that and make a really good set of notes that you can study from.